from our homework that we had last night, worksheet number 6. Specifically, we'll do questions 4 and 5 right now. Number 4 says 2 identical charges are separated by a distance of 1 meter. There's a repulsive force of 3.6 newtons acting between them. What's the magnitude of each of the charges? How are we going to find the value of a charge when we're looking for 2 of them? Well, because they're both the same, we can call it the same thing, right? If instead of calling it Q1 and Q2, let's call it Q and Q, since they're both the same, and then just solve for Q. Now, that still doesn't make it easy, but it does simplify it a little bit here. I'm going to say F is equal to K Q1 Q2 over R squared, or F is equal to K times Q over R squared, or F is equal to K. How can I simplify that? What's Q times Q? Q squared. Good. How many people said Q squared? Good. How many people said 2Q? Yeah, that's an easy thing to do, right? But that's adding, right? Q plus Q is 2Q. Q times Q is Q squared. So we rearrange this to solve for Q. The R squared goes up. The K goes down. And then we're going to square root that. Eventually we will. There we are. Q is equal to the square root of F times R squared over K. So F is 3.6 newtons. R squared is 1.00 squared. And K is 8.99 times 10 to the 9. Okay, let's figure that out now with the calculator. Let's say 3.6 times 1 squared. Let's divide that by 8.99 times 10 to the 9 plus equals, and now let's square root that. You get a value of 2.00 times 10 to the negative 5. Now let's charge on both of them, right? Because they're both going to be the same. Good? How many people ended up getting that? Okay. That's actually pretty good for seeing a question like that for the first time. That's pretty good that as many of you that did got it. Yeah.
Would one be negative, one be positive because it says they're repulsive?
No, if they're repulsive, then they both have to be the same charge, right? Both positive or both negative, and we don't really have any way of knowing whether it's positive or negative, just that they're both the same. Okay, let's take a look at number 5. An electron and a proton are 5 times 10 to the negative 29 meters apart. By the way, in a hydrogen, that is the average distance of the electron, is 5.29 times 10 to the minus 29 from the nucleus of it. That's pretty close, right? Calculate the magnitude of the force that acts between them, and what's the acceleration of the electron if it's free to move? Some of you I know are having a little bit of trouble with the charges. They're on your data sheet, right? 8.99 times 10 to the 9. Look in your data sheet for the charges. We get 1.6 times 10 to the minus 19 for the electron, and 1.6 times 10 to the minus 19 for the proton. Isn't the charge of one of them the electron negative?
No.
No, well it is,
Well, yeah.
but not in the equation, right? We never sub the sign of the charge into the equation because we don't want to get mixed up with direction here. So make it positive, get the magnitude. R is 5.29 times 10 to the minus 29. Let's calculate this one now on our calculators. Let's say 8.99 times 10 to the 9 times 1.6 times 10 to the minus 19 times 1.6 times 10 to the minus 19 equals, and then let's divide that by, use some brackets here, 5.29 times 10 to the negative 29, and then let's square that, everything inside the bracket. Gives me 8.2241 times 10 to the 28 newtons. How come I wrote down 4 decimal places there? Because I'm not done the question, right? I have to find acceleration still, and maybe I'm going to use that force. In fact, I know I'm going to use that force, right? To find acceleration, the force needs to be with you. The force needs to be with you. And once the force is with you, what would Yoda say?
Then put it over mass.
Not exactly. He would say more
put it over the mass, you will. A.
Yes, something like that, yeah. Divide the force by the mass, you will. And that gives us the acceleration. We're looking for the initial acceleration of the electron, so let's use the mass of the electron. If we were finding the acceleration of the proton, we'd use the mass of the proton. This gives us 9.03 times 10 to the 58. If we were looking for the acceleration of the proton, would we expect it to be more or less than the acceleration of the electron? This is the electron, right? I wasn't asked to calculate the acceleration of the proton, but if I was, Megan, if I was, would the acceleration of the proton be more or less?
It's heavier than it is.
Okay, good enough. Good enough. You don't need to look it up there. Yeah, the proton is heavier, and you can see that by looking on your data sheet, right? So therefore, because it's heavier, the acceleration will be lower. Same force, smaller acceleration. Let's do one more example before the end of class here. Number 3 says, look, we got 3 charges in a row here. We want to find the net force on the middle one due to the 2 end ones. This one, as you can see here, is positive. This one is positive as well, and this one is negative. Now, I don't know about you, but it's tempting when we have 3 charges to say F is equal to K, Q1, Q2, Q3 over R squared instead of K, Q1, Q2 over R squared. Is that going to work for us? No. If K, Q1, Q2 over R squared gives us units of newtons, and that's what we want because we're talking about forces, right? Then Q1, Q2, Q3 over R squared is not going to give us newtons. Rather, it's going to give us newtons times coulombs, and that's not a unit for force. So that's just not going to work. We can't just arbitrarily change an equation because it would make it easier to solve the problem. It would, but it's not going to be right. So what are we going to do? Any ideas here? We want to find the net force on this middle one here, on this middle one right here, due to the other 2. What are we going to do? Good. We're going to find 2 forces here. The force of object 1 on 2, and then the force of object 3 on 2, and then we're going to combine them. But how do we know how to combine them? Add or subtract. We got to pay attention to direction here. So what I want to do first before I actually do that, Lucas, is draw a free body diagram. You guys remember in physics, from Physics 20 what a free body diagram is?
Yeah.
It shows all of the
Forces
acting on an object. So let's draw the forces acting on object 2, first caused by object A here, okay? A and B, they're both positive. Pretend C is not even there, right? It doesn't exist as far as we're concerned right now. Just A and B. They're both positive. Do they attract or repel? Enrique, do they attract or repel? They repel, good. They push each other away. That means that B will be pushed away from object A. We're going to call that FAB. FAB, the force of A on B is to the right. Now, there is a force of FBA, the force of B acting on object A, and it's going to be equal and opposite to the force of A on B, right? But I'm not even going to draw that in. I'm going to get rid of that because, although it's there, I'm not trying to find the force on object A, so why would I clutter up my diagram with another force that's there but not relevant to the question? So don't draw that. It's there, but it's not relevant, unless you're trying to find the force on object A. Then, obviously, it would be relevant. All right. Now, let's pretend A isn't there, and let's look at C. C and B, one's positive, one's negative. Do they attract? Then do they attract or repel if we got positive and negative? They attract, good. So that means that B will be attracted or pulled towards C. FCB, the force of C on B. Now, C will also be pulled towards B, right? But that's not relevant to us because we're not trying to find the force on object C. So let's not clutter up our diagram with a force that's not necessary. We got 2 forces acting here. One force caused by A on B, that pulls or pushes B to the right, and then another force of C acting on B, which pulls B to the right. Now let's calculate both of these forces. FAB is KQA QB over R squared, which is 8.99 times 10 to the 9, times A is 2 microcoulombs, that's 2 times 10 to the minus 6 coulombs. B is 3 times 10 to the minus 6, divided by R, which is 2.0 meters squared. Let's calculate that value. Here's my numerator. Divide that by 2 squared, which is 4. Gives me a value of 0.013485. Okay, there's the first force, A on B. The force of C on B is 8.99 times 10 to the 9 times 3 times 10 to the minus 6. Don't forget that exponent, right? Said that the standard unit is coulombs, but that's a really big unit of charge, right? And we often see microcoulombs or millicoulombs or nanocoulombs. We always got to convert to coulombs, though. We're dropping the sign of the charge there. That was really a negative 1 microcoulombs, but we'll make it a positive for the equation. Divide that by, what's the distance there? 1.5. Okay, let's calculate that one now. 8.99 times 10 to the 9 times 3 times 10 to the minus 6 times 1 times 10 to the minus 6 divided by 1.5 squared, using a value of 0.01199. What do we do with these?
Add them up.
Yeah, we add them up, and they're both going to be positive here. How do you know they're both going to be positive?
Because their force is on, or they're going the same way.
They're going the same way. They're both acting to the right. And that's why we do our free body diagram. If one was to the right, one was to the left, we'd make one of them a negative. But since they're both to the right, we'll make them both positive. When we do that, the net force, the sum of those forces, just like in Physics 20, is this plus this one, 0.0255. Is our net force there. Well, if we drew these to the right and we made everything positive there, then we'll just assume right is positive. That would be okay. Yeah, as long as you recognize that right means positive for you and left means negative. Is that all right? When I walk around, people are working on these questions. It never fails. Some people don't draw the diagram because some people think they're smarter than that. I don't have to draw the diagram. I could just do this without a diagram. I'm here to tell you, you're not smarter than that. You need to draw a diagram. I need to draw a diagram. Okay, it increases our chances of getting this correct dramatically if we draw the picture, the free body diagram that shows the forces in which direction they act. Okay, draw that picture. Calculate those forces like I have, and then add them up. Just make sure that you add. Put a negative in if necessary. Not in this case, but if necessary. Now, one more quick little thing before I set you free to work here. This is a perfect example of a question that illustrates for us why we don't sub the sign of a charge. If I had to sub the negative in there for the 1 times 10 to the minus 6 coulombs, what would I have gotten for FCB?
Negative.
I would have gotten negative 0.01199, right? What would the temptation have been? To add them together with the negative there, right? That would have been an easy temptation to fall into, an easy trap to fall into, right? And that would have given us the wrong answer. We don't want to put a negative for the charge in there because we're probably going to get it mixed up with direction if we do. So just drop the sign of the charge, plug it in, and figure out the direction the way that we did, not with an equation. All right? The homework for tonight is question 6 and question 7 and 8 on worksheet number 6 that you were working on before, and also worksheet number 7, just question number 1. Now, there are 4 parts to question number 1, but the good news is some of the calculations you do in question A and B can be used for questions C and D, so it becomes just some addition and subtraction once you get past the first couple of those questions. All right?